State-of-the-art solar thermal power generation relies on mirror designs such as parabolic troughs, what they call parabolic troughs, where they concentrate the solar energy in the form of heat onto a working fluid. And that fluid is typically a synthetic oil that then drives a steam engine. In contrast to our approach with a solar thermal photovoltaics, it's a solid state energy conversion process. Instead of using a Rankine cycle to generate the power, we utilize the photovoltaic cell. So really, it also still requires potentially concentrations to get to the high temperatures, but there's no fluid operating in the system at all in this case. It's really the simplicity and scalability of the approach that is the advantage of a solid state type system. Instead of having a lot of pumps, say, working to move the fluid across various pipes, then here it's all can be contained nicely and there's no real moving parts. And that can improve the reliability of these types of systems. And you can also make different types of form factors that can be varying from compact to kind of larger scales. In a traditional steam power plant that takes advantage of solar thermal, these are usually hundreds of megawatt type scale type units for power generation, right? Because it really, in order for the steam power plant to be efficient, it cannot be that compact, right? The losses are significant at smaller scale, so they have to be really large scale type implementation. The way these photonic crystal structures work is they're actually patterned on a surface. So there can be layers of these materials such as silicon dioxide that creates constructive and destructive interference such you can tailor the spectral characteristics. Or they can be what they call two-dimensional photonic crystals. They can be cavity structures etched into material. And this is what allows us to now manipulate what the sunlight comes in the broad spectrum at various wavelengths to a specific wavelength that is targeted for the PV cell. Right, so the efficiencies are what govern the difference between a, say, single junction photovoltaic cell like in silicon, which is what's commonly used now, and then the idea here with our solar thermal photovoltaic cells, the photovoltaic cells can take advantage of a larger spectrum of the sunlight to get higher efficiencies. So typically in a single junction photovoltaic cell, you're capped to about 30% in terms of efficiencies. The theoretical limit of these solar thermal photovoltaic devices is over 80%, right? And that's the difference between capturing part of the spectrum versus the entire spectrum. Another significant advantage of solar thermal photovoltaics or using thermal processes is storage. So we know that sunlight is not 24/7 and that we need a way to store the energy. Batteries are significantly more expensive than thermal means to store energy. And that way, this becomes technology with the solar thermal photovoltaics that become quite dispatchable in nature, relatively more easily compared to that of a photovoltaic.